All right, let's do some examples. So, first of all, here's a couple of rules to work with. These are just a couple of just basic rules that come from some very basic functions like power functions and exponential functions. So first, the first rule here is if you have the limit as x approaches infinity of 1 over x to the n, where n is a positive number, that will be 0. And the idea there is like if you're dividing by a power function and the power function's input is approaching infinity, the output is going to be approaching infinity. So you're dividing by numbers that are approaching infinity. And when you divide by those larger and larger numbers, you approach 0. So that is a nice handy dandy rule we can work with. By the way, if x is approaching a negative infinity, this is also true so long as the function is defined for negative values, which it only would be if you were dealing with a rational number with a denominator that's not even. If you had like x to the power 1/2 down here, then negative numbers would be giving you complex outputs, and it would not apply. So as long as it has a domain that includes negative numbers, then this could be negative infinity, and it would still be 0. The second rule is for the e to the x function, which this is true for e to the x, but this is also true, in fact, for any exponential function a to the power x when a is greater than 1. So for the e to the x function, it looks like this, and there's a horizontal asymptote over here at 0, but just on the left side. Right? On the right side, it diverges to infinity. So the rule is the limit as x approaches negative infinity of e to the x is 0. Okay? It's got that asymptote just on the left. Now, if you change it to e to the negative x, that is going to reflect it over the y-axis and move that horizontal asymptote over onto the other side. So if you make the power negative x instead of positive x, now the asymptote occurs when you take the limit as x approaches positive infinity, which is the right side. That would equal 0. So those are our rules to work with. Now let's start doing some examples. For the first example, we're going to use rule number 1. So the first example we're going to look at is the limit as x approaches infinity of a rational function. Now I'm going to throw out a rational function, and I'm going to do several examples of rational functions. But for the first one, let's do 2x squared plus x minus 3 over x squared plus 3x minus 5. This is a rational function where the degrees are matching one another. The degree of the numerator and the degree of the denominator, that is, are both equal to the same thing, which is 2. So, first of all, before we do anything to this, let's just analyze what's going on. The numerator, if you take the numerator polynomial by itself, it's a quadratic polynomial. If you just graphed that, you'd get a parabola. And that value is going to be approaching infinity as x approaches infinity, because it has a positive leading coefficient. So the numerator, its end behavior, as x approaches infinity, that limit would be infinity. So I'm going to write numerator approaches infinity. The denominator is also a polynomial, also a quadratic polynomial, so that's also a parabola, positive leading coefficient, so this parabola opens upwards. So as x goes off to positive infinity, the end behavior on the right is also infinity. So the denominator is also approaching infinity. Okay, so that means that this entire thing here appears to be approaching infinity over infinity. Now that is an indeterminate form. So, reminder. Back in Chapter 2, we would occasionally encounter situations where the limit appears to be 0 over 0, right? Like there were situations where we'd attempt direct substitution, and we'd get 0 over 0. And we'd say that's an indeterminate form. It doesn't actually mean anything. It doesn't mean it's undefined. It doesn't mean it's equal to 0. It doesn't mean anything at all, because actually you can cherry pick examples where it's undefined, or it's 0, or it's equal to 10, or it's equal to negative 2/3, or whatever. There's literally, it could be anything. So this type of, when I say this is an indeterminate form, indeterminate means not determined. It doesn't determine anything. Knowing that this is giving us this indeterminate form, doesn't give us any information about what the limit actually is. It just means we've got to try a different strategy. Okay, so back in chapter 2 we had 0 over 0. Now in this section we're going to see we have infinity over infinity. This may have come up back in chapter 2 as well. I don't know. But they're both examples of indeterminate forms. So that means we have to work with this in some other way. We're going to do a little bit of algebra manipulation, just like we did back in chapter 2. It's a slightly different manipulation than we did back in chapter 2. We're not going to try to cancel anything. We did a lot of canceling, like factoring and canceling and so on, back in chapter 2. This time we're going to do something a little different. We're going to take the numerator and denominator, and we're going to multiply them both by the same thing, so that we're multiplying by 1, and we're not changing the function. And what we're going to multiply by is 1 over x squared. 1 over x squared. And I choose x squared because x squared is 2 is the degree of both the numerator and denominator polynomial. I'm taking the highest power of x, and I'm going to basically divide the numerator and denominator each by that highest power of x. And the result here, after we distribute, we're going to have to distribute, right? So, and there we go. After distributing, the first term is going to become a constant because it's going to have x squared divided by x squared. So in the numerator, the first term is just 2. And then the second term, we have plus x divided by x squared, which becomes 1 over x. And the third term is going to be minus 3 divided by x squared. In the denominator, our first term is x squared over x squared. That's 1. Okay? The second term is 3x divided by x squared. One of those x's is going to cancel, and we're going to have 3 over x. And the third term is going to be minus 5 divided by x squared. So that's what we get after distributing. And the reason this is useful is because now, if we split up the limit and take the limit of the numerator divided by the limit of the denominator, I'll show you what that looks like. We're going to have limit as x approaches infinity of 2 plus the limit as x approaches infinity of 1 over x minus the limit of 3 over x squared. And then in the denominator, we'll have the limit of 1 plus the limit of 3 over x and minus the limit of 5 over x squared. And now, oh, by the way, I should say that, just because we're taking the limit as x approaches infinity doesn't mean all of our other limit laws don't still apply. So they do still apply. So I've just applied the laws where we split the limit over the quotient and then split the limit over the addition. And now the limits of these constants are still equal to those constants, just like just like if you were taking the limit as x approaches anything else. The limit of 2 is just 2, right? So this is just going to be 2. And the limit of 1 is just 1. But then each of these other ones, they are limits of some constant multiple of 1 over a power of x, a positive power of x. So every one of these other terms is just 0. And now this is clearly equal to 2, which is our limit. So this strategy takes us from something which is indeterminate, right? Is infinity over infinity. It takes us to something which is which has all these 1 over a power of x, all these terms where we have 1 over a power of x, and every single one of those terms is going to approach 0, and we just have this ratio of constant terms, which turns out to be the ratio of leading coefficients from the two polynomials in the rational function. So if you remember back in college algebra, I taught you that as a general rule, but I didn't really explain why. Well, this is why. And now we have the limit language and understanding to really understand why it is that it approaches the ratio of the leading coefficients. So that's it for that example.